electromagnetism this semester. I think it's going to be a fun course, and it's also going to be a rigorous course. The expectation is that you'll work hard, as in all physics courses you always do. And the prerequisites for this course is a good understanding of calculus, calculus 1, and if you're taking calculus 2 concurrently, that is along with this course, then that would really help. So the website for this course is given here. So on this website, on the left column, there is a link to my teaching. And from here you will find a link to electricity and magnetism. Fall 2015. You will also find a link on this navigation column to the previous offering of this course when I taught it the previous year. So the lectures will be video recorded, the videos will be uploaded, but there is no substitute to attending the class in person, because the kind of learning that would happen in the real class cannot be matched or paralleled by just sitting offline back in your cozy rooms and looking at the videos. So the atmosphere in the classroom will be totally different from what you would see in a pre-recorded video. So during this week, I will also finalize the TS for this course. My office hours will have recitations, tutorials. Remember, it's an intensive course, so you'll have to work really hard. But my job here is to make that intensity somewhat enjoyable and pleasurable for you as well. There will be homeworks, two kinds of homeworks, individual homeworks and collaborative homeworks. There will be quizzes, mostly multiple choice, with some short questions as well. There will be a midterm and final exam. So the course outline is already uploaded onto this website. I will not upload material on LMS. So all the material will be uploaded on this website. So don't expect to see course packs on LMS. And as far as the textbooks for this course are concerned, unfortunately, I couldn't find an appropriate textbook. There are two books that are helpful, but basically this course emerges from my own understanding of electromagnetism. I generally take a lot of ideas from some articles that are published in some reputed journals. So it's basically stepping out of my own investigations of how to teach this course in an effective manner. However, there is one book which is by Sabieh, and the exact name can be found on the website. You can find this book in the library as well, and this book is really helpful for problem solving. Okay. So in this course, we'll basically be dealing with, as the name suggests, electromagnetism, and we're looking at a fundamental force of nature, which is the electromagnetic force. Now there's a great urge in all of physics and science to unify forces, and you already know that there are four kinds of forces. We have the strong nuclear force, the electromagnetic force, the weak nuclear, and the gravitational force. So all basic interactions between matter can be described in terms of these four forces. Now, have you ever wondered what these forces are? If you have a nucleus, say the nucleus of lithium, which has 3 protons inside it, 3 protons and 4 neutrons. Okay. Lithium, 3 protons, 4 neutrons to give a mass number of 7 and an atomic number of 3. Now these 3 protons are all positively charged, but they are confined within a very small volume. The volume of the nucleus is typically of the order of femtometers, which is about 10 to the power minus 15 meters. So now you have 3 positive charges in close vicinity to one another, and they're all jam-packed into the nucleus. So one would imagine that these 3 protons will mutually repel one another, and the nucleus cannot be stable. The nucleus should, in most cases, just explode in a big explosion. But that doesn't happen. Lithium is a stable atom. You can find lithium ores. Likewise, you go up to iron 56, numbered 56. All of these atoms are stable, but they have a large number of protons that are packed into a tight volume. So even though the repulsive forces are extremely strong, that is, the electromagnetic forces are strong and they're repulsive in this particular case, there has to be an attractive force that keeps the nucleus bound together. That attractive force is called the strong nuclear force, and it acts between gluons. But this nuclear force is strong, but it's operative on very small distances. So outside the nucleus, this strong nuclear force does not make its presence felt because it's a short range force. However, on a short scale where it is operative, it's about 100 times stronger than the electromagnetic forces, than the electrostatic forces. So if I put this on a scale of 1 in terms of strength, this would be about 100 times stronger than the electrostatic forces. Remember, magnetic forces are a special form of electric forces. They don't have a distinct identity. So when we study special relativity, electric forces can be transformed into magnetic forces in different frames of reference. We'll learn more about this in due course. Then we have the weak nuclear force. It's a very weak force and it's operative on, once again, small distances. So on a scale in which the electromagnetic forces are numbered 1, this would be about 10 to the power minus 12 to 10 to the power minus 13. The relative strength of this force is so small. And then the fourth force, the fourth interaction, which occurs between any 2 massive objects, is the gravitational force. But it's extremely weak, of the order of 10 to the power minus 30 on this scale. But we see that the Earth is attracted towards the Sun. It's kept in orbit. The Moon is kept in orbit around the Earth. Even though it's a very weak force, but it appears that the effect of this force is quite pronounced. Remember that the electromagnetic forces are 10 to the power 30 times stronger than the gravitational forces. Yet we do not see an electrostatic or electromagnetic pull towards the Sun. We do see a gravitational pull. Can anyone point out the reason behind this? The mass is very large, but still the gravitational force per se cannot outweigh the electrostatic interaction. Exactly, because the net charge on the Sun is 0 and the net charge on average on the Earth is 0. So even though these electrostatic forces are really large, yet the net charge on these massive bodies is almost 0. So the electrostatic forces just cancel out. So even though the gravitational interactions are quite weak, they're very feeble, they're minuscule on this scale, they're so small, yet the effect of gravity is quite pronounced because the other effects are too small to make a pronounced effect. So these are the four interactions that define most of all of the interactions that we have, and in the present course we'll be focusing our attention on this interaction, and we'll make a concerted, systematic effort in understanding these interactions. Now, one of the goals of this course is to understand a set of equations that was formulated 150 years ago, and those equations are called Maxwell's equations. So if I just write down these equations go as follows. E dotted with dA over a closed area is Q over epsilon naught. This is one equation. Don't worry if you don't understand what this equation means at the moment. I'm just going to present what these equations look like. Over a closed area. This is an alternative way over a closed path. Third equation. And the fourth equation is, so I'm going to write these equations and then I'll take a couple of minutes of telling you the importance of these equations. Closed path So these four equations, formulated towards the end of the 19th century, are called Maxwell's equations. Now Maxwell, James Clerk Maxwell, was a Scottish physicist, one of the greatest minds that we've ever seen, and he synthesized four equations. Synthesis means that you have different people coming up with different ideas, and then you put everything together in a coherent, unified whole. So if you look at a beautiful monument like the Taj Mahal, it has minarets, it has domes, it has these cloisters, it has a platform. So all of these components are beautiful in their own right, but when they are composed together in the form of a beautiful, symmetric, grandiose whole, then the real beauty emerges. And this is called synthesis. So that's what Maxwell actually did. These were four equations or four principles that were formulated by different people in different periods of time. This was formulated by Gauss, Carl Friedrich Gauss. This first equation. This second equation is just the historic origins of these equations are not well known, so it's not ascribed to any individual, but it's generally called the Gauss's law for magnetism. But this second equation is not conventionally ascribed to any one particular person. So it just stands as it is. And you can see a symmetry between this equation and this equation, with the difference that the right hand sides are different. This is a finite number, whereas this is 0. B is a magnetic field, A is an area, E is an electric field, Q is a charge, epsilon naught, I'll explain what this means. So these are two of the Maxwell's equations. Now this third equation is due to Faraday. It's also called the Faraday's law. Gauss and Faraday were from the 19th century, early 19th century. This particular equation is a combination of two minds. One is the mind of Ampere, who came up with this term, mu naught I is a current. And this second term, which is a more complicated looking term, mu naught epsilon naught times the derivative of this integral, is due to Maxwell himself. Generally, this equation is called the Ampere's law, or the Ampere-Maxwell's law. So all four of these equations are called Maxwell's equations. And towards the zenith of this course, which will happen of course towards the final exam, you will have learned all four of these equations. Now if you don't understand what these equations mean, it doesn't matter. The purpose of this course is to have you appreciate the profound consequences of these equations and how they apply in an astounding way to all electrostatic, electromagnetic, time dynamic, electric, magnetic, all kinds of electromagnetic interactions, and how these equations are generally considered to be the bloodline of our existence, because electricity generation is based upon these equations. Wireless communication is based upon these equations. The computer technologies are based upon these equations. So these four equations are a complete unified set of principles that describe all of electromagnetism. Okay? And if you graph these equations with quantum mechanics, you get quantum electrodynamics. You get a more unified framework. So if at the end of this course you can explain these equations, interpret them and describe them in simple English, Urdu, Pashto, or any language that you speak, to your younger brother, to your parents, to your friends, then that means you actually learned something from this course. So the goal of this course, if I may say, is to understand these four equations. It looks like a very easily stated goal, but the path is somewhat treacherous. You have to do a lot of work to understand these equations. Okay? Alright. So this sets out the learning objective of this course, understanding Maxwell's equations. Now I would like to start off with the concept of charge and what charge really means. आप किसी भी वक्त मुझसे सवाल पूछ सकते हैं during the class and try to attend all classes. जी. Sabieh is an author. Sabieh and Moses wrote this book on modern physics, but it's not that book. It's a different book, Physics for Scientists and Engineers. जी. Any more questions? So I would like to start off with the concept of charge. It's always good to take notes. We'll draw a lot of sketches in the classroom. There will be a lot of graphs that we will draw. I will ask you to do a few problems inside the classroom as well. So always be attentive. Okay? And there will also, of course, be some practical demonstrations inside the classroom as we go along at the appropriate times. Now, the concept of charge is something really familiar. We have these elementary particles. For example, we have the leptons, such as the electron. Now, the electron is a fundamental particle, and it has a negative charge, and its charge is fixed at some value which we know with a certain precision. We can increase the precision with which we know the charge, but this charge is approximately in SI units 1.602 into 10 to the power minus 19 coulombs. And by convention, we say that the electron carries a negative charge. There's nothing more to convention than this. You can also have the antiparticle to the electron, which is called a positron, which has a charge plus E. Same mass as an electron, but the opposite charge. You could also have other particles like muons. Now, muons come into varieties. You can have a positively charged muon and a negatively charged muon. And the muons are more massive than electrons, about 280 times, 270 times more massive than electrons, and they carry the same charge as electrons, so they have smaller charge to mass ratios. Then you can have pions, which are charged particles. They could be charged particles. They could be neutral as well. Then you have quarks, which carry fractional charges like 1 over 3 E, or 2/3 of the unit charge. And they are composed inside a proton in such a way, in such a number, that the charge on a proton is plus E, and the neutron turns out to be neutral. So the origin of charges lies in nuclear physics. It lies in the charges that are carried by these elementary particles. Okay. And we can also notice that charge in reality is quantized and is discretized. Because the particles that carry charge, they are discrete particles in a way. Now, what's the concept of a point charge? Now, you've taken a modern physics class. You studied the hydrogen atom and the electron inside the hydrogen atom. There's one electron inside the hydrogen atom, okay? Now, where is that electron inside the atom? Could anyone tell me where the electron is inside the atom? Or how would you attempt to answer this question? You cannot tell. Alright, what can you tell? The probability where you can find the electron. Can you find the electron at the nucleus? Alright, so if I draw a distribution, and this is R, which is the distance from the nucleus, and here I have the radial probability distribution. That is the probability of finding an electron at a radius r within a small shell dr. This is the probability of finding the electron at a certain point inside the nucleus. So if I draw this graph, what will it look like? If the electron is in the ground state, if the atom is unexcited, so the graph that you obtain looks like this. There's zero probability of finding the electron at r equals 0, which corresponds to the nucleus. This distribution function goes up, and then it decreases, it wanes, it goes down. And what is this point where the distribution function is maximized? What's this point? That's the Bohr radius, A0. About 0.5 angstroms. Alright? So the maximum probability of locating the electron is at the Bohr radius. Now this question of where is the electron inside the atom? Is not a legitimate question. It's not a legal question. It's not a justifiable question if you talk in terms of quantum mechanics. Because what we have is a wave function of the electron. And if you look at the wave function and find the modulus squared of that wave function, multiply that with r squared to get the radial probability density, this is what you will obtain. So this distribution is really r squared, the wave function modulus squared. So this is proportional to the probability of finding the electron at a certain radius. It's maximized at the end, at the core radius, but the probability is non-zero up to infinity, even though it goes to very small values. So this question of where is the electron is not a legitimate question if you study quantum physics. The electron is in a way everywhere. Agreed? So where is the charge inside the hydrogen atom? And how much is the charge? If the electron is really everywhere, you can't tell where the electron is, because this is really the probability distribution function. Where is the charge then? Remember, the hydrogen atom, the electron, must have a finite amount of charge. The charge cannot be infinite. The charge is simply minus E. Now this is a finite number, finite amount of volume of charge. Now where is the charge inside the hydrogen atom? If the electron is smeared out, where should the charge be? Ji? So the negative charge is everywhere. All right. It's quantized, yes, but where is it? In space. आप नीचे क्यों देख रहे हैं? क्या देख इधर? देखिए, if the electron is really everywhere, then the charge is also spread out in space. But the point is that this is a distribution function a priori, which means that you haven't measured. Now you can perform a measurement of finding out where the electron is with some microscope that can probe the electron at the atomic level. Such a microscope is called a scanning tunneling microscope, STM. With the help of an STM, you can find out where is the electron, which means you can perform a measurement. So when you perform a measurement, a real experiment in the laboratory, you will never find out the electron to be spread out. You will just collapse. You find the electron at this position, or at this position, or at this position, or at any distance along this radial line. Okay? And if you perform the experiment on identical hydrogen atoms, all of them in the ground state, what you will obtain is a histogram or a distribution function like this, which means that in most cases you will find the electron in the vicinity of A0. But occasionally you could find the electron spread out at different radial distances. And then if you make a histogram of all of these occurrences, you make a histogram, the number of times the electron is found here, 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 and then if you connect these with, connect the heights of these bins with the solid line, you will reproduce the probability distribution. So even though the electron is spread out, when you perform a measurement, you pinpoint a precise location of the electron. This is the nature of quantum mechanics. Likewise for charge, the charge is really spread out before you've made a measurement. But when you have a detector that detects the electron, it will always measure the entire amount of charge on a single electron, which is minus E. So all the energy, all the charge will lump together, will bunch up and hit onto the detector when you perform a measurement. So even though the charge is spread out, when you perform a measurement, the detector will always give the same amount, the same energy inside the click, which corresponds to the charge minus E. So all the energy bunches up together and hits the detector. This is called a collapse of a wave function. Now what do we mean by a point charge? A point charge is just an idealization. If you probe the electron on the atomic scale, then the charge is spread out and it has a certain probability of appearing at different distances inside the atom. So it's just like having a small atom, and if you're at the size of the atom, charge will appear to be non-point like. It will appear to be spread out. So it's just like, you must have read the story of Gulliver. Gulliver was a giant, and he went into an island in which pygmies lived, and we call them the Lilliputians. So the Gulliver was talking to the Lilliputians. So if we talk to the Lilliputians, we have to talk in their language. So if you look at the atoms face to face, that is, we approach atoms on their face value, that is, the probing apparatus probes the atoms on the atomic scale, then charge will not be point-like. Charge will have a wave function like distribution or a probability distribution that is smeared out, and it will only collapse the wave function to one point or the other. But if you're talking about big objects, we are at the scale of microns or centimeters or millimeters or meters or kilometers, then this wave functional description of electrons is not really needed. Then we can treat the electron for all practical purposes as having infinitesimal volume, zero volume. So the electron doesn't have a volume because it's so big that the volume of the electron over which the wave function is spread is just minuscule. It doesn't appear, it doesn't show up. So on the scale that we're going to talk about in this course, all the charges are point-like. Okay? So that is what is meant by a point charge. A point charge is a charge that doesn't have a volume. Because we are so big and the charge is so small that we could easily say that the charge is spread over zero volume. This is what is meant by a point charge. Now, one of the important laws, so-called laws in electromagnetism is Coulomb's law. Now, there are different kinds of laws in physics. Coulomb's law is an empirical observation. Most laws are empirical, that is based upon repeated observation. You perform experiments a large number of times and you find out a certain pattern of behavior, and you put that pattern in the form of a mathematical equation. Okay. So this is an empirical law. What this law states is that if you have 2 point charges, now point charges should have zero volume, but on the blackboard I'm drawing some big charges. Because if I draw points, you will not be able to see them. So this is just a conceptual rendering of a point charge. It's actually really small in volume. Okay, I can just draw a point as well. Now if this charge is Q1, this charge is Q2, and both of them are positive charges, and the distance between these point charges is, say, R, and I would like to find the force on this charge. Now suppose these charges are put inside, embedded inside a matrix, and they cannot move. Okay? So they're put inside a rigid framework in which they can't move, but they exist, right? So they are studded into their place, but they can't move. Now they're in vicinity, this charge will exert a force on this charge. Now since both of them are positive charges, this force will be away from the direction of this charge. So if I make a line between Q1 and Q2 and draw a vector, then this vector is going to point in the opposite direction to the line. So this is a hypothetical axis that joins the charges. This force is along this line of action and it's pointing away from this charge. So let me call this force F. It acts on charge 2 and it's due to charge 1, F21. And since it's a vector, I put the vector sign on top of it, F21. Now Coulomb's law simply states that this force, F21, is given by some constant which I call 4 pi epsilon naught into the product of the magnitude of these charges divided by the square of the distance between the charges. And since force is a vector, this force must point in a certain direction. Let me call that direction r hat. It's a unit vector. It doesn't have a magnitude. The magnitude is just 1, but it specifies the direction of the force. Now this is an empirical observation. You repeat the experiment a large number of times on different systems, you get this behavior. I would just like to emphasize the empiricity of this by putting a tilde on top of it. It's approximately equal to this. In fact, this 2 could be 2 plus epsilon, where epsilon is a small number. And there are research groups in the world that actually find out whether this epsilon is truly 0 or not. So it's an approximately inverse square dependence. It's an inverse square law, like the gravitational law. And you can never tell whether this epsilon is truly 0 because experiments will never reveal something that is truly 0. There is no such thing as true 0 in experiments. What you could at the most say is that this epsilon is smaller than some numbers, say 10 to the power minus 5 or 10 to the power minus 6. You can upper bound the value of epsilon. So you're close to inverse square law dependent. Now this is a statement of the Coulomb's law. And in most cases we just ignore this epsilon. Likewise, you have the Coulomb's law for gravitation as well. An inverse square law for gravitation. Now this constant epsilon naught is called the permittivity of free space. And its value is approximately 8.85 into 10 to the power minus 12 Coulomb square divided by Newton meter square. So some authors prefer to call this constant K. I will not use the value K because K is reserved for something else in most cases, but many authors would call this K, some constant. Now if you would like to find the force on this charge, then that force is given by, it's symbolized by F, force on charge 1, exerted by charge 2. So it's exerted by the presence of the second charge. It's a vector. Again 1 over 4 pi epsilon naught Q1 Q2 r squared. The magnitude remains the same, and now the unit vector is minus r hat. It's pointing in the opposite direction, right? So this is just minus F21. So the force on this charge is in this direction along minus r hat. If I define this to be r hat, the forces are equal in magnitude, opposite in direction, and they act on different objects. So it's just a manifestation of Newton's third law of action. and reaction. Alright, now this factor of 4 pi appears quite strange. Now this factor of 4 pi is for historical reasons, and it's in a particular system of units called SI, the international system, and it keeps everything in good shape. It keeps everything consistent. So this, you can just imagine that this is just a convention, 4 pi. And this equation here, the Coulomb's law, which is statement of Coulomb's law, is written in SI, the international system, where the forces are in newtons, the charges are in coulombs, and the radius is in meters. The distance is in meters. And this value of epsilon naught is quite interesting, because if you take this value of epsilon naught, multiply it with another constant mu naught, which is called the permeability of free space. This is something we learn as well when we study magnetism. If you take the permittivity of free space multiplied with the permeability of free space, then what, lo and behold, you will get 1 over the square of the speed of light. So the permittivity and the permeability are fine-tuned in such a way that their product is related to the speed of light. And in fact, all of these fundamental constants, epsilon naught, mu naught, the charge on an electron, Planck's constant, these values, and of course, by virtue of epsilon naught and mu naught, the value of the speed of light. So these fundamental constants are all fine-tuned by nature. They're so fine-tuned that if their values were off by a fraction of a percentage, this universe would have been different. So that is why some philosophers believe in what is called the anthropic principle. The anthropic principle states that all the fundamental constants have values that are fine-tuned and cherry-picked in such a way that this universe could exist in the way it really exists. And we could have a habitable environment in the form of the Earth, which is just in the biosphere, at the right distance away from the sun, and which has the right conditions so that life could emerge and human beings could exist. That is why it is a human-centric principle. Anthro means humanism or humans. It's called the anthropic principle. Remember that all of science has a historical component to it. There's history behind science. We are part of a large historic lineage. It's not that we're working in isolation, neither geographically nor temporally. We are part of a history of science. And then there's a philosophy of science as well. So this is the Coulomb's law. Now the Coulomb's law is our starting point for the discussion. But there's another concept, which is the concept of a field that is more universal, more embracing. Field. Now there are different kinds of fields. Suppose we take this room. And this room is defined by 3 axes, X, Y, and Z. So this is an X-axis, a Y-axis, and a Z-axis. And you take a point inside the room, any point inside the room, and put a temperature sensor there, which senses the temperature at precisely that point. Let me call that temperature at that point T. It's a symbol for a temperature. Now this temperature would be different at different points, unless the temperature is uniform or homogeneous throughout the room. So the temperature is different at different points. So it is parameterized by these 3 variables, X, Y, and Z. So the temperature will change with X, Y, and Z. Right? But then the temperature could also change with time. Like the air conditioners can be turned on and off, and there are diurnal variations within the day. So there's morning, there's day, night, everything changes with time as well. So there's another parameter which is time, small t. So the temperature in fact will be dependent on these 4 variables, and each point on this grid will have a certain value of T. Okay? So this temperature represents a field. It's called a field. And the temperature is a scalar quantity, it doesn't have a direction. So you just have a thermocouple at different points, and the thermocouple negotiates the temperature. You get a variation of temperature time-wise and space-wise inside the room. So this variation of temperature is called a field. The temperature represents a scalar field. A field is just a physical quantity that can be parameterized by space variables and time variables. Okay? So this is an example of a scalar field. You can also have, you've seen weather maps. So during the monsoon season, you generally see maps of this kind. So these maps are called atmospheric pressure maps, and these lines are called isobars. So all the points on this line represent the same pressure. Bar means pressure. All the points on these lines represent pressure. Say this is 100, it's quite a big number. Say this is 10 atmospheres. So all the points in space that are along this line are at a pressure of 10 atmospheres. These points represent 9 atmospheres, 8 atmospheres, 7. So all of these points are on an isobar, and this is, pressure here is being treated as a field. It's a scalar field. The pressure doesn't have a direction. What's the atmospheric pressure here? It's 10 atmospheres. Here it's 10 atmospheres. This could be Lahore, Gujranwala, Islamabad. This could be Faisalabad. So this is a spatial variation that has been plotted somehow in the form of these contour lines, which are called isobars. So this is really, here pressure is being treated as a field, P, which depends upon X, Y, and Z. In this case, since it's a weather map, we have a longitude and a latitude. Okay? And we also have time. So this is the map at one instance in time, 8 a.m. in the morning. It's a scalar field. Now if you look at, so in between the pressure could be interpolated, so in between it could be 9.5. You cannot draw all the isobars because the map will be too cluttered. So this is an example of a scalar field. Now this pressure difference causes a particular flow of air. That flow of air is quantified by the velocity of air. So at each point you can draw the velocity of air, and one way to draw the velocity of the air, since it's a vector, is to draw an arrow. So you draw an arrow that is normal to this isobar. So you draw an arrow here, which I am representing in pink, which shows the velocity of air at this point. And it's normal to this isobar. So at each point on the isobar, you can draw these velocity vectors. So there will be some velocity here as well. And of course the velocity is pointing from the high pressure to the low pressure region. And these velocity lines will show the direction of airflow. So I can draw velocity vectors all the way, normal to the isobars. And so on. Now velocity is also a physical quantity. This time it's a vector quantity. So what I've drawn on this map, I've drawn small arrows to represent a vector field. This vector field V is the velocity field. It's a vector. And once again, it depends upon longitude, latitude, and is a function of time. So this vector field, this velocity field, is an example of a vector field. Another way to draw this field is, instead of drawing these arrows, I can just connect these arrows by streamlines. This is another way of drawing fields, vector fields. I can connect these arrows by continuous lines called streamlines. So now we have two prescriptions of drawing vector fields. I can either draw arrows at each point, or I can connect all the arrows in the form of continuous lines. The length of the arrow represents the strength of the field at that point. The number density of these streamlines, that is how these streamlines are bunched together. If they're close together, the field is high. If they're far apart, the field is low. Okay? So these are two possible ways of representing vector fields, either through arrows or through continuous lines. And their bunching or density tells you the strength of the vector field. The length of the arrows represent the strength of the vector field. Okay? Now we would like to talk about electric fields. जी ऊंची बोलो, सबको आवाज है. Because the velocity is the gradient of the pressure. Okay? Motion is always normal to the gradient of concentrations. Velocity is the gradient of the pressure, the gradient is normal. Okay? Achha, with this background, another example of a vector field, for example, is water flowing through a pipe. Now this is a pipe and I've drawn a longitudinal section of the pipe. Now if the water flow is laminar, laminar means there is no turbulence. The flow of the velocity is small, smaller than the Reynolds number. Okay, so it's a laminar smooth flow. What's going to happen is that if you take the water flowing through this pipe and you focus on the particles of water, which are really water molecules, at the edges, the velocity of a particle at the edge, at the outer periphery, will be really small, almost zero. And the particle that's in the exact middle will have the maximum velocity. And the velocity will fall off as you approach the walls of this pipe. So this kind of flow is generally called a Newtonian flow. It happens for certain kinds of fluids, Newtonian fluids, in laminar flow conditions. So this is also a vector field, now representing velocity. Okay? And if you want to draw streamlines to represent this vector field, you will draw lines that are closer together in the center, and then they wane off, or they just become less dense towards the center. So the same vector field can either be represented by arrows or by streamlines. And I would also like to put arrows on top of these streamlines to represent the direction of the flow. So these are just two alternative ways of representing vector fields. Now the electric field is also a vector field. Suppose I have a point charge, Q. Now what I would like to do, I would like to draw a hypothetical sphere around this point charge. A fictitious sphere. It doesn't exist really, it's just the figment of my imagination, I draw a sphere. And the center of this sphere is the point charge itself. Now I take a point on the sphere and I find out what is the direction of the electric field here. Now what do? Out of my pocket, I take out a test charge, a small charge, a test charge from somewhere, and I place it here. Generally this test charge QT is by convention a positive charge. I place it here. So this is a probe charge. With the help of this test charge, I would like to find out what the electric field is due to the original charge. So this is just a probing charge. मैं शरारत के तौर पर पानी में पत्थर फेंक रहा हूँ, देखो पानी को क्या होता है, कोई ना कोई पत्थर मुझे फेंकना पड़ेगा देखने के लिए कि पानी की क्या कैफियत है. So I'm just taking a test charge and putting at the point P where I want to find the electric field. Now when I bring in this charge, this test charge will exert a force on this charge, original charge. So I assume that nothing of this kind happens, which means that this original charge is fixed in position. It's studded in a rigid lattice or a frame which does not allow it to move. Even though force may exist, it doesn't accelerate. So it remains there in its position. Or in other words, the test charge is so small that it doesn't affect this original charge. Now if I take this test charge and place it here, I find the direction of the force on this test charge. This force will be Ft. Right? And it will be given by 1/4 pi epsilon naught. The original charge Q times the test charge divided by r square, where r is this distance, right? Now this is of course a vector, so it's going to point in a direction r hat, which is radially outwards. This is radially outwards. Okay, so this is a force on this test charge. Now you might come up with a different test charge of a different magnitude. A third person might come up with a different test charge. But this charge should give you a field that is independent of what kind of test charge you bring in. Okay, because we're looking at the properties of the field produced or synthesized by this charge. So what you would need to do, you would take the test charge Ft and divide this by the magnitude of the test charge you bring in. So what you will get is 1/4 pi epsilon naught Q over r squared in a certain direction. And now this expression is independent of the amount of test charge that you brought in. Okay. So now you would like to, this is called the electric field at point P due to charge Q. And to find out that field, you bring in a test charge and place it at your point of interest and find out the force on that test charge divided by the magnitude of the test charge. Now you can find the electric field at any point on this sphere. And this electric field, of course, will have the same magnitude on the sphere because the distance of all of these points from the center is the same. But the directions will all be different. All of these electric fields will be pointing radially outwards, like the spokes of a wheel. Okay? So this is the electric field pattern at this particular distance. Now if I try to expand this a little bit, I don't have to fix my distance. I can have any distance that I like. This charge plus Q. I take a sphere, then I take a larger sphere, a smaller sphere, and I want to find the electric field throughout space because of this charge. So what I would do, I would take spheres of varying volumes, of varying radii. So first, I find out the electric field at this outer volume. I get some electric field, again radially outwards. The length of the arrows relatively represent the strength of the electric field inside, in an inner circle. The strength will be larger because there is a 1/r square dependence. right? So I can draw electric field vectors here. Now they will be larger in size. So what I'm drawing is the electric field due to the charge plus Q. As you go closer and closer towards the charge, the electric field becomes larger. So this is the prescription or the description of the electric field in terms of arrows. And you can map the electric field in the entire expanse of space. This electric field E will be a function of space, and it can also change with time. If it doesn't change with time, it's called a static field, and if it changes with time, it's called a dynamic field. Now the alternative prescription for drawing the electric field, as you know, is through continuous lines. So you could draw lines like this. And you draw arrows on top of these lines to show the direction of the electric field. Here the fields are bunched closer together. The density of field lines per unit area is larger, so the electric field is larger. So both of these are equivalent sketches of the electric fields. Now one of the beauties of the Coulomb's law, and in fact most of physics, is linearity. What does linearity mean? Or superposition. In order to describe superposition, let me come up with an example of an ion, which is iron hexacyanoferrate. Okay, it's a negatively charged ion. What does this ion look like? There's an iron ion with a charge of +2, and then in a square plane there are 4 negatively charged cyanide ions which are equidistant from the iron ion. So each one of these represents a cyanide ion. Cyanide. A cyanide ion is simply a carbon atom, triple bond with a nitrogen atom, and one dangling bond with which it latches onto the iron ion. But there are 6 of these. 4 are symmetrically disposed around the iron ion, and the 5th one is at the top along the axis, and the 6th one is at the bottom. Now all of these are negatively charged, negative charges, all 6 of these ligands. Negative, negative, negative. And these charges will have an electric field of their own that spreads throughout the volume of the molecule. And if you want to find the electric field at the position of the iron ion, you could find the electric field due to the individual charges. Each one of these will be a vector, and then you take the vector sum. This is called the principle of superposition or linearity. So in order to find the electric field at the location of the iron ion due to this ion, the electric field will point in this direction towards the negatively charged ion, because it's a negative charge now. The electric field due to this ion will point diametrically opposite. The electric field due to this ion will point in this direction. The electric field due to this ion will point in this direction. So all 4 of these vectors are arranged in a plane, and the mutual angle between these vectors is 90 degrees. Now the electric field due to this ion is vertically upwards, and the electric field due to this ion is vertically downwards. So now you have 6 vectors that are symmetrically disposed, and if you take the vector sum of these 6 vectors, what do you get? 0. So the net electric field at the position of the iron ion is 0. even though this iron is surrounded on all sides by negatively charged anions, negatively charged cyanide ions. So now you have to respect these vectors. These are vectors, not scalars. They have certain directions, and you have to take the resultant of these vectors. If somehow this ion is in a solution, and the solution has a membrane in it, and the membrane is positively charged, and these ions sit on the membrane. So if this is our membrane, it could be a cell membrane or another membrane that is used in fuel cells, and if this is positively charged, then the symmetry will be disturbed. And there are two ways to look at it. You can use the superposition principle and just find out the electric field due to this positively charged membrane at the site of this iron. And this electric field will be pointing in this direction because this is a positive charge. So the electric field will point away from the positive charge. Okay, because if you place a positive test charge here, the force will be directed in this direction. So the next electric field at this point, due to the presence of this membrane, will be in the positive direction. Another thing that will happen is that a force will be exerted on this ion in the downward direction, and a force will be exerted on this ion in the downward direction. But this force will be larger in magnitude than this force. Okay, because the distance between these charges is small, and there is a 1/r² dependence on forces. So what will happen is that this symmetric octahedral molecule will no longer be octahedral, it will be a skewed molecule, it will be stretched in the vertical direction. And due to that stretching, an additional electric field may appear here, because then this ion will be further away from this ion. So all kinds of things can happen. But the point that I would like to make is that you have to respect the superposition principle. If you have many charges inside some volume, Q1, Q2, Q3, and so many of them, and you would like to find out the electric field at some point P. So what you would do, you would find the distance of this point from this charge, from all of the charges. Okay? And you would find the direction of the electric field due to each infinitesimal charge first, and then you would integrate. So your final result would look something like this. 1/4 pi epsilon naught. The individual charges Qi, each one of them is Qi. You divide by Ri, the distance of point P from each of the charges squared. You find the unit vector of each charge from the point P radially outwards, and you take the vector sum. I goes from 1 to the number of charges. So this is the total electric field at point P. If you have a discrete distribution of charges, the charges are discrete. But if you have a volume which is charged on a whole and you cannot discretize the charges, then what you would do is you would replace this summation with an integral dq over r squared 1/4 pi epsilon naught. And I'll talk more about integrals in the next lecture. Alright, so please feel free to ask questions. With time, we'll get more comfortable with one another. Hanji.
I always thought that electric charge was like a property that's associated with certain particles. So what do you mean when we're talking about one test charge placed next to a test charge? The charge by itself, what is that?
You could have an object that has been charged. For example, I can take this piece of chalk, I can rub it with a piece of cloth, and it will pick up a charge. It will be some object that has acquired some charge. A cloud acquires charges by rubbing against other clouds. The clouds become electrified, and that's how lightning occurs. One of the oldest known phenomena. So there are different ways of picking up charge. And I'll show you practical demonstrations of how charges can be built up. One last question. How do I convert this into an integral? I'll talk more about this. So do you understand this? So I'll talk more about this. Don't worry. This is just making the charges smaller and smaller, then this summation becomes an integral. Have you done integration in calculus 1? Alright. Alright, inshallah, see you on Thursday.